Some of history's most brilliant ideas disappeared for 1,000 years. This journey explores 15 ancient inventions that were lost to history for millennia, revealing how our view of progress is often an illusion. By the end, you will see the past not as a simple story, but as a landscape of forgotten genius. We will encounter concrete that repairs itself and a mechanical computer that mapped the stars. How could such advanced knowledge simply vanish? What does the loss of these technologies tell us about our own civilization's legacy? What forgotten masterpiece from our own time might one day puzzle the future? The seafloor near Antikythera held a secret for 2,000 years. In 1901, sponge divers working in stormy waters stumbled upon the wreck of a Roman cargo ship. Among the statues and ceramics, they recovered a lump of corroded bronze and wood, so encrusted it seemed like little more than junk. It was catalogued and largely forgotten for decades, a curious artifact in a museum storeroom. No one could have guessed this unassuming object would force us to rewrite the history of technology. It became known as the Antikythera Mechanism. For nearly half a century, its true nature remained a mystery. Then researchers began to look closer. Using advanced imaging techniques like X-ray tomography in the 1970s and beyond, they peered through the centuries of corrosion. What they saw was breathtaking. Inside that lump were intricate bronze gears precisely cut and interlocking, arranged in a complex system of dials and pointers. This was not a simple ornament, it was a machine, a clockwork computer built around 100 years before the Common Era, designed to model the cosmos. The device was a portable astronomical calculator. By turning a hand crank on the side, an ancient Greek scholar could make the gears spin. Dials on the front would then display the positions of the sun and moon against the backdrop of the zodiac. It could predict lunar phases and solar eclipses with remarkable accuracy. One dial even tracked the 4-year cycle of the Panhellenic Athletic Games, a kind of ancient Olympic timer. It was a user manual for the heavens, all contained in a wooden case about the size of a large shoebox. The sophistication is staggering. The mechanism used a series of differential gears, a technology historians once believed was invented in the 16th century. It accounted for the irregular orbit of the moon using a clever pin and slot design. To put this in perspective, nothing of similar mechanical complexity would appear again in Europe until the great cathedral clocks of the 14th century. That is a knowledge gap of over 1,400 years. Historian Derek J. DeSolla Price, who dedicated his career to studying it, famously stated that finding this device was like discovering a jet engine in the tomb of King Tut. It was that far ahead of its time, so how did something so advanced simply vanish? The mechanism was not a one-off toy. Cicero, the Roman philosopher, wrote about similar devices created by the thinker Archimedes. This suggests a tradition of geared astronomical models in the Hellenistic world, but that world collapsed as the Roman Republic fell and the empire faced its own challenges. The specialized knowledge required to build and maintain such precise instruments likely faded. The libraries that held the plans burned. The craftsmen who understood the mathematics passed away without apprentices. The single surviving mechanism sank to the bottom of the sea, taking its secrets with it. Its rediscovery poses a profound question about the nature of progress. We often think of history as a straight line, with each generation building on the last. But the Antikythera Mechanism is a powerful reminder that knowledge is fragile. It can be concentrated in small communities, written on perishable materials, and lost in the chaos of war, economic decline, or simply the passage of time. This one artifact proves that the ancient Greeks possessed a mechanical genius we never credited them with. It forces us to wonder what other masterpieces of engineering, now turned to dust, once existed. And it makes the next lost invention, a building material that defies the ages, all the more compelling. The dome of the Pantheon in Rome is a silent witness to a forgotten science. Cast in the 2nd century, this vast, unreinforced concrete ceiling has not only survived for nearly 2,000 years, it has actively defied the elements that crumble our own modern structures. Its secret lies not in superior force, but in a lost recipe, a self-healing concrete that modern engineers are only now beginning to understand. While our contemporary bridges and overpasses require constant repair, often succumbing within decades, Roman harbors submerged in seawater for millennia remain astonishingly intact. This durability stems from a deliberate and brilliant formula, one that used the very environment as a strengthening agent. Ancient builders mixed lime with a special volcanic ash called pozzolana, named for the town of Pozzuoli near Mount Vesuvius where it was sourced. When this mixture was combined with seawater, a remarkable chemical process began, known as the pozzolanic reaction. Instead of simply drying out, the concrete underwent a long-term transformation. Tiny plate-like crystals grew within its matrix, filling in microscopic cracks as they formed. Even more incredible, when seawater seeped into new cracks, it would react with the remaining lime and ash to create more binding material, effectively healing the wound. Materials scientist Marie Jackson has spent years studying this ancient concrete, describing it not as a static material, but as a living rock that grows stronger with time. Modern Portland cement, in stark contrast, is brittle. When water infiltrates its pores, it can rust the steel rebar inside, causing the concrete to crack and spoil from within. The Roman formula required no steel reinforcement. It was designed to thrive in the very conditions that destroy our own infrastructure. The knowledge was deeply practical and locally sourced, utilizing the unique geology of the Italian peninsula. But with the gradual fragmentation and decline of the Roman Empire, the centralized engineering expertise and organized trade networks needed to produce this material faded. The recipe was not so much stolen as it was forgotten, a victim of societal collapse and the loss of institutional memory. Recent studies of submerged Roman piers, still solid after 2,000 years of wave action, offer a blueprint for a more sustainable future. Researchers are actively trying to reverse engineer the ancient mix, hoping to create new, durable concretes for seawalls and coastal infrastructure. This pursuit forces a humbling reflection. How could a formula that built empires and defied the sea simply slip from our collective hands? It underscores that technological advancement is not a one-way street. Sometimes the most profound solutions are not ahead of us, but behind, waiting in the ruins for us to look closely enough. And just as this concrete has preserved structures, another lost invention was designed to preserve something far more ephemeral, capturing light itself in a dance of crystal and flame. A weapon that burned on water became the ultimate safeguard of an empire. Greek fire was the terrifying secret weapon of the Byzantine Empire, a liquid flame that could not be extinguished by water and that clung relentlessly to wooden ships and the men aboard them. First used decisively around the year 672, its deployment was a spectacle of horror and awe. Historical chronicler Theophanes described it as a fire that was blown from tubes, roaring as it rushed across the waves to ignite enemy fleets. For centuries, this technological marvel secured Byzantine naval dominance, particularly in the defense of the great city of Constantinople. The psychological impact was as potent as the physical destruction. Imagine the dread of an opposing sailor seeing a stream of fire arching toward your vessel, knowing that dousing it with seawater would only make it burn more fiercely. The exact formula was a state secret of immense power, guarded with obsessive zeal. knowledge was compartmentalized, likely held only by the ruling emperor and a single family of chemists or artisans. Recipes were never written down in full, passed orally from one generation to the next. This absolute secrecy, while a brilliant short-term strategy, proved to be its long-term undoing. Theories about its composition are educated guesses based on fragmentary clues. Most researchers believe it was a crude petroleum-based mixture, perhaps from surface oil seeps around the Black Sea, combined with resin or sulfur to make it sticky. Some accounts suggest quicklime, which ignites upon contact with water, could explain its fearsome reputation. It was deployed from bronze siphons mounted on ship prows, pressurized by large pumps, and likely ignited by a flame at the nozzle. It could also be hurled in clay pots like grenades. Its most famous demonstration came during the Great Arab Siege of Constantinople in 717. A massive Arab fleet aiming to crush the Byzantine capital found itself trapped in the city's narrow harbor. Byzantine ships fitted with their fire-spouting siphons swept in. The result was a catastrophic inferno. The Greek fire spread across the water's surface, engulfing the invasion fleet and turning the tide of the conflict. It was a victory that preserved Christian Europe for centuries and cemented the weapon's legendary status. Yet, by the 13th century, the knowledge was gone. The specialist artisans may have died without passing on the full secret during a period of political turmoil. The final emperors may have simply never learned it themselves. The very policy of extreme secrecy that protected the weapon ultimately erased it from history. Modern attempts to recreate Greek fire are just that, attempts. Without a definitive recipe, we can only approximate its effects. This loss forces us to reflect on a difficult paradox. How do we balance the need for security with the need for preservation? The Byzantines chose absolute secrecy to maintain a military edge, a decision that saved their empire repeatedly, but also guaranteed their ultimate invention would vanish. It poses an ethical question as well. If we could rediscover the full formula today, should we? The power to create an unstoppable incendiary weapon carries a moral weight the ancients never had to consider on a global scale. From this destructive force that was lost to excessive secrecy, we find a beautiful contrast in an invention lost to the opposite, a technology so openly brilliant it was used to adorn everyday life before fading from memory. The quiet hum of electricity feels uniquely modern, a force we have only recently learned to harness. Yet a simple clay jar from ancient Mesopotamia whispers a different story. Discovered in 1936 near Baghdad, this unassuming artifact looks like nothing more than a storage vessel from about 200 years before the Common Era. But inside, it held a curious assembly, an iron rod encased by a copper cylinder, sealed at the top with asphalt. To German archaeologist Wilhelm Koenig, who first studied it seriously, it resembled something profoundly anachronistic, a primitive galvanic cell, a battery. The principle is straightforward, a basic electrochemical reaction. If the jar was filled with an acidic electrolyte, something as common as vinegar or fermented grape juice, a chemical reaction would occur between the two different metals. Electrons would flow from the iron rod to the copper cylinder through the acidic solution, creating a small but measurable electrical voltage between the two metal terminals. Experimental recreations by researchers and even modern hobbyists have confirmed this function. A replica can produce just over 1 volt of electricity, not enough to power a light, but enough for a subtle, tingling sensation. So what possible use could such a faint current have held for people living 2 millennia ago? One compelling theory is electroplating, the process of using electricity to coat one metal with a thin layer of another, like putting a layer of gold onto a silver object. Some artifacts from the same period show fine gilding that is difficult to explain with known chemical techniques of the era. Another possibility is medical application. using the mild current for analgesic or therapeutic purposes, a practice hinted at in some ancient texts describing the use of electric fish to numb pain. Skeptics offer a more mundane explanation, suggesting the jar was simply a secure storage container for sacred scrolls, with the iron and copper acting as protective sheaths, the asphalt as a seal. The truth is, we have no definitive answer. No wires, no electrodes, no clear instructions have been found alongside these jars. Their existence is an isolated puzzle, a single data point without a connecting narrative. This isolation is the real mystery. If this was indeed a purposeful battery, why was the knowledge not expanded upon? Why do we find no evidence of circuits, no lamps, no motors? The answer may lie in the nature of innovation itself. An invention, no matter how clever, requires a context to flourish. It needs a perceived need, a community of tinkerers to improve it, and an economic or cultural reason to adopt it widely. Perhaps the Baghdad Battery was a brilliant accident, a curiosity understood by only a few temple priests for use in rituals, creating a shimmer on statues to inspire awe. Its secret may have died with them, never connecting to a broader technological system that could have nurtured it into something more. This artifact forces us to reconsider the spark of discovery. It suggests that the fundamental principles of our world have always been there, waiting to be noticed. A civilization might stumble upon a profound truth, use it for a single, narrow purpose, and then let it fade away, not from a lack of intelligence, but from a lack of connective tissue between idea and application. From this solitary spark of potential, we turn to a lost material that wove together the practical and the sublime, a fabric so legendary it was said to be worth its weight in gold. A blade that could bend without breaking and cut through stone became the stuff of medieval legend. European crusaders returning from the Holy Land brought back terrifying tales of swords wielded by their adversaries, weapons of incredible sharpness and resilience, their surfaces flowing with a pattern like rippling water or wood grain. This was Damascus steel, a metallurgical masterpiece whose secrets were forged and then lost over centuries. Its origin was not the Syrian city it was named for, but ancient India, where a unique form of high-carbon steel called woots was produced in small clay crucibles. The process was an alchemy of earth and fire. Iron ore was combined with specific organic materials like leaves and wood in a sealed container, then heated in a charcoal furnace for hours. This slow, controlled process allowed carbon to diffuse evenly into the iron, creating a material with a very high and uniform carbon content. The resulting ingot, a lump of Wootz steel, was a treasure traded across the known world. It was these ingots that made their way to Middle Eastern forges, where master smiths performed the true magic, the pattern welding. The smith would repeatedly heat, hammer, and fold the steel. This wasn't just to shape it, it was to manipulate its very crystalline structure. The careful cycles of heating and slow cooling caused the carbon within to form into microscopic structures, hard carbide bands within a softer, more flexible iron matrix. Modern research, like that led by metallurgist John Verhoeven, used advanced electron microscopy to peer into the atomic heart of ancient Damascus blades. What they found was astonishing. The steel contained carbon nanotubes, tiny structures of incredible strength, formed over 1,000 years before modern science even conceived of them. These structures are what gave the steel its legendary properties, its superplastic ability to withstand bending, and its ability to hold a razor edge that could cleave through lesser metals. The watery pattern, the damask, was a visual map of this exquisite internal architecture, a signature of perfection. Yet by the 18th century, the knowledge to create true Damascus steel had evaporated. Several factors conspired in this loss. The specific iron ores from India, rich with just the right trace impurities like vanadium, became depleted or inaccessible due to shifting trade routes. The crucible method was a slow, costly artisanal process. ill-suited for the mass production demanded by changing armies and warfare. Perhaps most critically, the knowledge was held in the hands and eyes of master smiths, passed down through apprenticeships without written formulas. When those lineages were interrupted by war, economic change, or simply a lack of worthy students, the nuanced craft, the feel for the heat and the rhythm of the hammer, died with them. Modern blacksmiths and materials scientists can now replicate the visual pattern, but creating a blade with the identical nanoscale structure and performance of the ancient originals remains elusive. We can analyze what they achieved, but we cannot fully recreate the journey that led them there. This loss is a poignant lesson in the intangible nature of expertise. It asks us how much of our greatest technology is not just in the blueprint, but in the hands of the maker. The decline of Damascus steel did not just mean weaker swords. It meant the extinction of a material science approach that viewed metal as a living thing to be cultivated, not just processed. As we leave behind this art of forged light and shadow, we find an ancient invention that sought to manipulate light itself, not with a hammer but with geometry and flame. Held up to the light, this ancient Roman cup performs a breathtaking transformation. From an opaque jade green, it glows a translucent, fiery crimson, as if the glass itself holds a captured sunset. This is the Lycurgus cup, a 4th century masterpiece of cage-work glass, or diatretum, where a thick outer shell is carved away to leave a delicate, lace-like network of figures standing in relief. But its true marvel is not merely in its intricate carving. It is in its color, a property engineered at a scale so small the Romans could never have seen it. They had, quite by accident, invented nanotechnology. The cup depicts the myth of King Lycurgus, entangled in vines for his defiance of the god Dionysus. In ordinary reflected light, the green glass makes the scene seem submerged, a murky underwater tableau. But when a light source is placed inside, or when light shines through it, the entire vessel erupts in a vibrant, wine-dark red, transforming the king's punishment into a vivid, dramatic spectacle. For centuries, this magical property was a beautiful mystery. Then, in the 1950s, scientists finally had the tools to look closer. Using powerful electron microscopes, researchers like Ian Freestone peered into the very fabric of the glass. What they discovered was astonishing. The Roman artisans had infused the glass with a precise mixture of gold and silver dust, but this was no coarse powder. The particles were unimaginably tiny, each one measuring only about 50 nanometers across, less than 1,000th the width of a human hair. At this infinitesimal scale, metals behave in strange and wonderful ways. When light hits these suspended nanoparticles, a phenomenon called surface plasmon resonance occurs. The electrons on the surface of the metal particles vibrate in unison with the light waves, absorbing and scattering specific colors. The size and composition of the particles dictate the color we see. The specific mix of gold and silver in the Lycurgus cup scatters green light when lit from the front, making it appear green. But when light passes through, it is the red wavelengths that are transmitted, creating that stunning internal glow. The manufacturing process behind this feat boggles the mind. Without any concept of the nanometer, Roman craftsmen somehow perfected a recipe. They likely began by grinding coins or leaf of gold and silver into a fine powder, then mixing this meticulously into molten glass. The heat and chemistry of the melt would then break the metals down into those crucial nanoparticles, a colloidal dispersion held in perfect suspension as the glass cooled. It was a triumph of empirical material science, achieved through generations of trial, observation, and guarded workshop secrets. This knowledge did not survive the fragmentation of the Roman world. The economic networks and specialized glass-making studios required for such luxury items collapsed. The Lycurgus cup stands as a solitary, magnificent accident, a piece of functional art that harnessed a scientific principle modern physics only began to explain in the 20th century. Today, its legacy is not in museums alone. The same principle of plasmon resonance, first observed in this ancient cup, is now the foundation for cutting-edge technology. It is used in ultra-sensitive medical tests that can detect a single virus particle, and in environmental sensors that identify trace toxins. The Romans used it to tell a myth in 2 colors. We use its physics to diagnose disease and protect our health. This raises a profound question about the nature of discovery. How many other ancient processes, perfected through craft and intuition, were manipulating the world at an invisible scale? The Lycurgus cup is a silent hint that our ancestors might have been nano-engineers long before they had the words for it. It suggests that the path to advanced technology is not always a straight line from theory to practice, but can emerge from the beautiful, persistent pursuit of an aesthetic ideal. From this intimate manipulation of light and matter, we now look to the heavens, where another lost invention sought to map the cosmos on a grand and mechanical scale. Buried in a German forest for over 3 millennia, a bronze disc waited to rewrite our understanding of the ancient mind. In 1999, 2 men using metal detectors on the Mittelberg Hill made a startling find, not knowing they had unearthed what would become known as the Nebra sky disk. Looted from its original archaeological context and later recovered in a police sting, the artifact's journey to legitimacy was as dramatic as its imagery. Scientific analysis, including studies of its metal corrosion and trace elements, eventually confirmed its astonishing age, placing its creation around 1,600 years before the Common Era. This makes it the oldest known concrete representation of the cosmos anywhere in the world. The disk is a stunning fusion of metalwork, astronomy, and belief. On a bronze plate about the size of a dinner plate, gold leaf symbols are arranged with clear intent. A large circle and a crescent represent the sun and moon. A cluster of 7 small dots is almost certainly the Pleiades star cluster. Along the edges, 2 arcs mark the sunrise and sunset points between the solstices, and a final arc at the bottom, often interpreted as a solar boat, suggests a mythological vessel carrying the sun through the underworld. Archaeologist Harold Meller, who led its study, describes it not as a passive picture, but as a sophisticated Bronze Age calculator. By holding the disk aloft and aligning it with the actual horizon, a knowledgeable user could determine the correct time to add a 13th month to the lunar calendar, synchronizing it with the solar year. This was not abstract science, it was vital, practical knowledge. Knowing when to plant, when to harvest, and when to hold key ceremonies meant the difference between a community's prosperity and its hardship. The disk is a physical embodiment of a world view where the cycles of the sky directly govern the rhythms of life on Earth. Its recovery hints at a vast, interconnected network of knowledge in prehistoric Europe. The copper likely came from the Alps, the gold from Cornwall in Britain, and the tin for the bronze from yet another distant source. This was no local trinket, it was a prestige object of immense value, likely used by a spiritual or political elite to demonstrate their exclusive connection to the celestial order. The symbols themselves speak to a remarkably enduring tradition. The Pleiades cluster, marked so prominently on the disk, appears in myths and agricultural calendars from ancient Greece to indigenous cultures across the globe, a testament to humanity's shared gaze at the same guiding stars. So how did such a profound, integrated system vanish? The knowledge was likely held by a small, elite class of astronomer priests. As Bronze Age societies collapsed due to climate shifts, migrations, and conflict, these specialized custodians of cosmic order may have disappeared. The disk itself was buried, perhaps as a ritual offering during a time of crisis, taking its operational secrets with it. Its rediscovery forces us to abandon the notion of prehistoric Europe as a backward place. It reveals a society capable of precise observation, complex metallurgy, and a deep philosophical synthesis of heaven and earth. We are left to wonder what other portable observatories, what other manuals of the sky were melted down for scrap or lie still undiscovered. This artifact reminds us that the drive to map the cosmos is ancient, and that sometimes the most advanced technology of an era is not a tool but a symbol. From this celestial guide meant to be held in the hands, we now descend to an invention that mastered the darkness far beneath our feet. Deep beneath the sun-scorched deserts of ancient Persia, a hidden river flowed. While the surface world baked, engineers of the first millennium before the Common Era were solving a problem of survival with breathtaking elegance. They mastered the art of pulling water from stone, creating the Qanat, a subterranean canal system that turned barren lands into gardens. This was not a feat of force, but of profound patience and communal genius, a technology so effective its basic principles have never been improved upon. The challenge was stark. Surface water in arid Iran was scarce and evaporated quickly under the relentless sun. But deep within the foothills of mountains, groundwater collected, fed by distant rainfall and snowmelt. The Persian solution was to tap this hidden reservoir and bring it to the surface where it was needed without losing a drop to the air. The construction of a Qanat was a monumental, coordinated effort. It began with locating a water-bearing layer, an aquifer deep in the alluvial fan of a mountain range. From this mother well, diggers known as muqannis began their work. They did not dig a horizontal tunnel from the destination backward. Instead, they plotted a gentle, downhill slope from the water source to the settlement, often many miles away. Along this line, they dug a series of vertical shafts, spaced about every 20 to 30 meters, down to the planned depth of the tunnel. These shafts served dual purposes, providing ventilation and a way to lift out excavated soil and rock. From the bottom of each shaft, teams of muqannis would then dig laterally, connecting the shafts to form a continuous, gently sloping underground channel. The precision of the slope was everything, typically a gradient of just 1 in 1,000. Too steep and the water would flow too fast, eroding the tunnel walls. Too shallow and it would stagnate. This gradient was maintained over kilometers using simple but effective tools like water levels and plumb bobs, guided by generations of accumulated experience. The result was a self-regulating system. Gravity alone pulled the cool, clean groundwater through the dark tunnel, emerging at the surface in a village or at the head of farmlands. Because it traveled underground, it was protected from contamination and, crucially, from evaporation. Historian Paul Ward English emphasized that the Qanat was more than an engineering marvel, it was a social contract. Its construction and maintenance required the sustained cooperation of an entire community, binding people together around the shared lifeline of water. This technology spread like roots through the ancient world, carried along the Silk Road to Oman, Egypt, and even Western China. The magnificent city of Persepolis, seat of the Achaemenid Empire, was sustained by a sophisticated network of Qanats, its grandeur literally underpinned by this hidden hydrological system. Yet the knowledge of building new Qanats has largely faded. The decline began with the introduction of mechanized deep well pumps in the 20th century. Electric pumps could extract water faster and with far less initial labor, tapping aquifers that Qanats could not reach. But this modern solution contained the seed of a new problem. Pumps allowed for the unsustainable depletion of groundwater, lowering water tables and causing many ancient Qanats to run dry. The slow, sustainable wisdom of the Qanat, which only drew what the aquifer could naturally recharge, was abandoned for immediate abundance. Today, many old Qanats still flow in Iran and elsewhere, cherished relics of a more balanced relationship with a scarce resource. Some communities are working to restore them, recognizing their value in a world facing increasing water stress. This raises a poignant question for our time. In our pursuit of powerful, immediate solutions, have we lost sight of technologies that work in harmony with natural systems? The Qanat asks us to think in terms of centuries, not seasons, and to value the communal effort that true sustainability requires. It is a masterpiece of slow engineering, a testament to the idea that the most advanced system is sometimes the one that quietly endures. Having explored this life-giving network hidden in the earth, we now turn our gaze upward to an invention that represents humanity's oldest and most enduring dream, the dream of flight. A wooden bird powered by steam took flight over ancient Greece. In the 4th century before the Common Era, the philosopher and mathematician Archytas of Tarentum crafted what may be history's first robot, an automaton known as the flying pigeon. Descriptions from later Roman writers like Aulus Gellius paint a picture of a marvel, a bird-shaped device that could flutter and move through the air for a short distance, tethered by a wire or string. This was not magic, but a deliberate experiment in pneumatics and mechanics, a tangible demonstration of principles that would not be formally explored again for nearly 2 millennia. The likely mechanism was elegantly simple in concept yet sophisticated in execution. Historians and engineers who have studied the accounts propose a design involving a sealed boiler within the bird's body. Water inside would be heated perhaps by a small, hidden flame producing steam. That steam, building pressure, would then be vented out through a rear orifice. According to Newton's third law of motion, which would not be articulated for over 2,000 years, every action has an equal and opposite reaction. The forceful expulsion of steam backward would generate a thrust forward, propelling the bird along its tether in a fluttering, avian motion. In essence, Archytas had built a reaction engine, predating the more famous steam turbine of Hero of Alexandria by hundreds of years. For Archytas, a leading figure in the Pythagorean school, this device was far more than a toy. It was a philosophical statement. He sought to demonstrate that the mathematical principles governing harmony in music and geometry also governed motion in the physical world. The pigeon was a bridge between abstract theory and observable reality, a proof that human reason could decipher and even mimic nature's laws. Its cultural impact was profound, a symbol of human ingenuity that lingered in the imagination of the ancient world. Yet no physical remains of the pigeon have ever been found. Its existence is known only through secondary texts, leading to centuries of scholarly debate. Was it a real working model or merely a thought experiment described so vividly it entered legend? In recent decades, modern engineers have put the question to the test. Using materials and methods available in Archytas's time, they have constructed working replicas based on the historical descriptions. These reconstructions have proven definitively that the steam-powered pigeon was not only feasible but functional. It worked. This validation makes its subsequent disappearance all the more puzzling. Why did this spark of robotic and aerodynamic genius not ignite a technological revolution? The answer lies in context. In the ancient Greek world, such inventions were often seen as demonstrations of philosophical principle or as wondrous entertainment for temples and royal courts. They existed outside any framework of practical application or iterative engineering. There was no concept of an aerospace industry, no demand for automated labor, no ecosystem to nurture this seed into a growing field of study. The knowledge was personal, tied to Archytas and his immediate circle, and like so many specialized arts, it faded when that circle was broken. It is a pattern we see repeated throughout history. Centuries later, Leonardo da Vinci would fill his notebooks with designs for flying machines, helicopters, and automata, ideas that were also functionally brilliant but remained unrealized in his lifetime. Both minds were limited not by imagination, but by the technological and economic milieu that surrounded them. The story of Archytas's pigeon forces us to ask a difficult question. How many revolutionary ideas have been born in isolation, celebrated as wonders, and then shelved because the world was not yet ready to receive them? It reveals a time when science and art were not separate disciplines, but intertwined expressions of a quest to understand a harmonious universe. This mechanical bird, then, is not a failure, but a testament to a brilliant flash of insight, a lonely prototype for a future that took a very long time to arrive. From this ancient dream of automated flight, we find an invention dedicated to a far more grounded pursuit: the permanent preservation of human thought. A clay disc, perfectly round and palm-sized, holds a spiral of silent voices. Discovered in 1908 in the ruins of the Minoan Palace of Phaistos on Crete, this simple artifact has become one of the world's most famous and frustrating mysteries. The Phaistos disc is not written, it is stamped. Using 45 distinct pictographic seals, an unknown hand pressed 241 symbols into the soft clay, spiraling inward from the edge on both sides before the disc was fired. We see human figures, birds, a fish, a shield, a walking stick, a beehive. Each tiny image is crisp and deliberate, arranged in clear groups, suggesting words or phrases in a structured script. This is not doodling, it is a deliberate, sophisticated system of recording information, created around 1,700 years before the Common Era. And it is utterly alone. No other object like it has ever been found, not in Crete, not anywhere. This isolation is the heart of the mystery. How could an entire writing system appear on a single disk and then vanish without a trace? The challenge of decipherment is immense. Normally, linguists crack ancient codes by comparing them to known languages, using bilingual texts like the Rosetta Stone as a key. The Phaistos disk offers no such key. We have no parallel text, no lengthy inscriptions on tombs or tablets in the same script to provide context or repetition. The sample size is vanishingly small, just 241 symbols, less text than a modern tweet. This has not stopped a century of attempts. Some researchers believe it records a hymn or a prayer. Linguist Gareth Owens, after decades of study, proposes that recurring sign groups may relate to a mother goddess, perhaps naming the divine figure known in later Greek myth as the Lady of the Labyrinth. Others suggest it could be a legal document, an inventory of palace goods, or even a board game. Computational analysis has been applied, searching for statistical patterns that might reveal a hidden language, but without more data, even powerful computers cannot provide a definitive answer. The debate over its origin is equally intense. Is the disk a local Minoan creation, or was it brought from afar? A diplomatic message or a trader's ledger from a lost culture? The clay itself is local to Crete, suggesting it was made there, but the script could still represent a foreign language pressed onto local material. The truth is, we may never know what it says. This profound uncertainty forces us to confront a chilling reality of history, the loss of voice. When a language dies, it takes with it not just words, but a unique way of seeing the world, a culture's poetry, laws, jokes, and prayers. The Phaistos disc is a locked library containing a single, tantalizing volume. We can admire its beautiful binding, we can count the chapters, but the story inside remains forever closed to us. Its undeciphered state is a powerful symbol of the gaps in our historical record, reminding us that the past is not a clear narrative, but a fragmented puzzle with most of the pieces missing. What knowledge of the Minoan mind, what epic or mundane message, rests eternally encoded in that baked clay? The silence of the disk is a humbling lesson in the fragility of human communication, a single artifact representing an entire technology of expression that was lost. Perhaps because it was known to only a few scribes, perhaps because the palace that housed its secrets burned and collapsed. From this intimate mystery of symbols pressed in clay, we now shift to a lost invention of staggering physical ambition, one that sought not to record nature, but to fundamentally reshape it. A wooden figure on a ceremonial chariot pointed unerringly south, no matter which way the wheels turned. In the courts of ancient China, as early as the 3rd century of the Common Era, this was not magic but a masterpiece of mechanical engineering known as the south-pointing chariot. Historical texts like the Song She record its existence in awe, describing how the figure's outstretched arm would remain fixed on the southern direction, even as the vehicle traveled for miles over uneven ground. This was a compass that worked without a single lodestone, a triumph of gears over magnetism, and its secret lay in a brilliant system of interlocking mathematics made physical. The invention is often credited to the ingenious engineer Marjan, who served the Wei dynasty. His chariot solved a fundamental problem of navigation. How could you maintain a constant bearing when your path was constantly curving? The answer was a differential gear assembly, a concept that would not appear in the West until the 19th century in early automobiles. The mechanism connected the two wheels of the chariot to the central figure through a series of precisely calculated gears. When the chariot moved in a straight line, both wheels turned at the same rate, and the gears cancelled each other out, leaving the pointer stationary. But when the chariot turned, say to the right wheel would rotate less than the left wheel. The differential gear set would measure this difference in rotation and transmit a compensating motion to the figure, rotating it to the left by exactly the same amount the chariot had turned to the right. This continuous, automatic correction kept the pointer aligned with its original heading. It was, in essence, a mechanical computer performing real-time calculations to solve a navigational equation. The chariot's primary role was likely ceremonial and symbolic, a dazzling display of imperial sophistication. Imagine an imperial procession winding through the capital. Envoys from distant lands would see this impossible sight, a guiding figure that never wavered, a powerful metaphor for the emperor's unwavering virtue and the state's perfect order. It was engineering as political theater, demonstrating that the Chinese court could literally master direction and, by extension, destiny itself. Variations of the chariot were reinvented several times over the following dynasties, each iteration a testament to the enduring fascination with this mechanical marvel. Yet, by the time of the Song dynasty, the technology began to fade from use. The reason for its obsolescence was the rise of a simpler, more portable, and more reliable tool, the magnetic compass. First used for geomancy and later for navigation, the lodestone spoon or magnetized needle required no complex gearing, no careful calibration, and could be used by a single person on a ship or on foot. The exquisite mechanical solution was rendered obsolete by a more elegant physical one. The south-pointing chariot was not forgotten because it failed, but because a better tool emerged for the practical task of finding direction. Its legacy, however, is profound. It stands as one of the earliest known examples of a differential gear system and a landmark in analog computation. It represents a path not taken, a world where complex mechanical analog computers, rather than digital electronics, might have advanced to solve intricate problems. This forgotten chariot asks us to consider the tools we abandon in our own rush toward simpler solutions. What nuanced understanding, what mechanical elegance do we lose when we replace a physical system with a digital black box? It reminds us that innovation is not always a straight line, but often a branching tree where some limbs, no matter how beautifully formed, simply stop growing. From this land-based wonder of geared guidance, we now set sail to discover an invention that turned the ocean's constant motion into a source of pure, automated power. The wind itself could play a symphony in the bustling city of Alexandria. In the 1st century of the Common Era, the engineer and mathematician Hero described a marvel that blurred the line between machine and muse, a wind-powered organ that filled the air with spontaneous melody. This was no simple wind chime, but a complex automaton, a fusion of art and engineering detailed in his collected works, the Pneumatica. It stood as a public spectacle, an early and breathtaking application of renewable energy, not for grinding grain or pumping water, but for creating beauty. Historians of technology like James H. Beck point to it as a pinnacle of the Hellenistic world's fascination with automata, devices that mimicked life or created wonder through hidden mechanical means. The design was brilliantly logical. A vertical windwheel, much like a small windmill, was placed to catch the prevailing breeze. As it turned, it drove a series of connecting rods and cranks, which worked simple piston pumps. These pumps forced air into a pressurized reservoir, a kind of primitive wind chest. From this reservoir, the air was then channeled into a set of organ pipes, each tuned to a specific note. The final, magical step was controlled by a rotating cylinder studded with pegs, much like a giant music box. As this cylinder turned, also driven by the windwheel, the pegs would trip levers that opened and closed the valves to the pipes. The wind, harnessed and directed, became the musician, playing a predetermined tune that repeated as long as the breeze blew. Imagine encountering this during a public festival near a temple or theater. The crowd hears music swelling on the air with no human in sight to play it. For a society that saw the gods in natural forces, this would have been a profound demonstration, a literal harmony between human ingenuity and the power of the wind. It was a celebration of leisure and intellectual triumph. Yet, like so many wonders from the great library of Alexandria's intellectual sphere, this knowledge faded into silence. The decline of the Hellenistic centers of learning, the fragmentation of the Roman world, and the loss of texts like Hero's own meant such complex devices were no longer built or understood. They became legends described in manuscripts that few could interpret. Modern reconstructions, however, have proven their feasibility, bringing the haunting sound of Hero's organ back to life after 2 millennia of quiet. This successful revival makes its historical disappearance even more poignant. It prompts a reflective question. Why did this concept of wind-powered machinery not spark an industrial revolution? The answer lies in purpose and perception. In the ancient world, such inventions were often seen as philosophical toys or religious wonders, demonstrations of principle rather than tools for practical labor. The economic and social structures that would demand the automation of work on a large scale simply did not exist. The wind organ was valued for its ore, not its output. Its loss speaks volumes about what a culture chooses to preserve. Technologies seen as vital for survival, like agriculture or warfare, are often maintained. Those created purely for spectacle, for intellectual delight or public entertainment, are more fragile, their continuance relying on stable, wealthy, and curious societies that can afford such luxuries. When those societies change, the beautiful and non-essential is often the first knowledge to be misplaced. The story of Hero's organ is a reminder that progress is not just about necessity, but about the space a civilization makes for wonder. From this automated music created for delight, we now examine an invention born from a far more urgent human need, the desire to heal and to see within. A detailed Sanskrit text from 600 years before the Common Era describes the precise removal of a cataract. This is the Sushruta Samhita, a medical compendium attributed to the physician Sushruta, and it presents a vision of surgery so advanced, so systematic, that its principles would not be widely recognized again for over 2 millennia. Within its pages are descriptions of more than 125 surgical instruments, meticulously classified into categories like blunt and sharp, made from iron and other metals. This was not a collection of primitive tools, but a sophisticated kit for procedures ranging from hernia repairs to bladder stone removal, and most famously, reconstructive rhinoplasty. The text details a procedure to reconstruct a nose using a flap of skin from the patient's own cheek. a technique that forms the very foundation of modern plastic surgery. It describes the use of curved needles for suturing, the importance of proper wound drainage, and even the use of ants' heads as natural clamps for intestinal surgeries, where the insect's strong mandibles would hold tissue together before their bodies were twisted off. Medical historian Dr. M.S. Velayathan emphasizes the text's remarkable systematic approach, outlining not just tools, but a complete philosophy of medicine. It divided surgery into 8 categories, described the ideal qualities of a surgeon, and laid out a rigorous training regimen. Students practiced incisions on gourds and fruits, learned to extract seeds from fruit pulp without damaging the pulp, and sutured on animal skins and cloth to develop a steady, precise hand. This was a holistic system where surgery was one branch of a larger tree of healing that included diet, herbal medicine, and lifestyle. Yet, this comprehensive knowledge did not flow uninterrupted into the modern world. Over centuries, the specific designs of many instruments and the nuanced techniques for using them faded. Several factors contributed to this fragmentation. Social changes within India, including shifting religious and cultural attitudes that sometimes placed ritual purity above physical intervention, may have diminished the status of hands-on surgical practice. The knowledge preserved on perishable palm leaf manuscripts was also vulnerable to the chaos of history, invasions, and the destruction of centers of learning, like the great University of Nalanda, led to the loss of countless texts. While the core principles of the Sushruta Samhita survived in parts, the living, practical tradition of its most advanced surgical art was fractured. The scale of this regression becomes starkly clear in one specific example: cataract surgery. Sushruta described a method called couching, where a curved needle was used to gently displace the clouded lens deeper into the eye, restoring a degree of vision. In 18th century Europe, by contrast, the dominant technique was a brutal and often blinding procedure known as needling, where the cataract was violently broken apart inside the eye with a sharp instrument, frequently leading to infection and total loss of sight. It was not until the late 1700s that European surgeons, learning indirectly from Indian medical practices, began to adopt safer, more refined methods that echoed Sushruta's ancient principles. This historical gap forces us to ask a difficult question: how does a civilization misplace a complete manual for healing? The story of Sushruta's lost tools reveals that medical knowledge is not just information, it is a craft. It requires institutions to teach it, a culture to value it, and a continuous line of practitioners to refine it. When that continuity breaks, even the most brilliant techniques can slip into obscurity, awaiting rediscovery by a future age that must then relearn what was once known. This recovery offers a profound lesson for our own time, reminding us that true healthcare has always been a blend of technical skill and holistic understanding, a balance we are still striving to perfect today. From these instruments that healed the body, we now turn to a device that sought to measure something far more elusive: the steady, invisible passage of time itself. 1400 years before modern seismographs, a dragon would drop a bronze ball. In the year 132 of the Common Era, the brilliant Han Dynasty polymath Zhang Heng presented the court with an object of both stunning beauty and profound utility: the world's first seismoscope. It was a large, ornate bronze vessel, perhaps as tall as a man, encircled by 8 dragons, each facing a cardinal or intercardinal direction. Below each dragon's open mouth sat a waiting bronze toad with its own mouth agape. The interior mechanism was a closely guarded secret, lost to time, but historical chronicles like the Book of the Later Han record its astonishing performance. The device was designed not to predict earthquakes, but to detect and indicate the direction of tremors too distant for human senses to notice. The chronicle recounts a famous incident where a dragon facing west suddenly released its bronze ball into the toad's mouth with a loud clang, though no shaking was felt in the capital. Days later, a messenger arrived from a region hundreds of miles to the west, reporting a major earthquake. The direction matched perfectly. The court was awestruck, viewing the instrument as proof of the emperor's heavenly mandate and his ability to perceive disturbances in the very order of the world. How could such a device possibly work without any electronic sensors? Modern engineers and historians, including the pioneering seismologist John Milne in the late 19th century, have proposed plausible reconstructions based on the sparse descriptions. The leading theory involves an inverted pendulum suspended freely inside the vessel. Imagine a heavy mass hanging from a rod, free to swing in any direction, carefully balanced in the center of the 8 dragon mechanisms. When a seismic wave from a distant quake arrived, it would cause the vessel to tilt slightly. The pendulum, due to inertia, would lag behind this motion, swinging toward the direction from which the tremor came. This swing would then trigger a clever lever or latch mechanism connected to the dragon facing that direction, releasing the ball held in its jaws. The ball would fall with a resonant clang into the toad's mouth, providing both a visual and auditory alert. It was a masterpiece of analog signal processing, converting the faintest Earth movement into a clear, unambiguous signal. The seismoscope was more than a scientific tool. It was a potent political symbol. In a vast empire where news traveled slowly, an early indication of a distant disaster allowed the court to prepare relief efforts and demonstrate benevolent governance, reinforcing stability. Yet after Zhang Heng's passing, the precise knowledge to recreate his device faded. The blueprint was never widely published, if it was written down at all. The expertise resided in one man and his immediate workshop. As dynasties rose and fell, this specific mechanical art was lost, becoming a legendary footnote in historical texts. Modern recreations, built on the pendulum principle, have proven the concept is sound and remarkably sensitive. This successful reverse engineering makes its historical disappearance all the more poignant. It prompts a reflective question about the trajectory of technology. Why did this elegant early warning system not spark a continuous line of development? The answer may lie in its purpose. It served the centralized need of an imperial court, not a broader scientific community. Without a framework of shared inquiry and iterative improvement, the invention remained a magnificent singularity, a trophy of genius rather than the seed of a field. In an age of digital networks and instant communication, Zhang Heng's seismoscope offers a different kind of lesson. It stands as a testament to low-tech, resilient design, a reminder that effective solutions can be beautiful, mechanical, and independent of fragile power grids. What might we learn from this ancient analog approach for creating simple, durable disaster detection in remote communities today? The dragon and the toad, frozen in bronze, remind us that sensing the unseen is an ancient human ambition. From this instrument that listened to the whispers of the earth, we now turn to a final lost invention that sought to capture the very essence of life, not through machinery, but through a forgotten chemical art. A hollow bronze sphere hissed and spun, a globe of steam and motion in an Alexandrian temple. This was the Aeolipile, or hero's engine, a first-century marvel that demonstrated the power of steam to create rotary force. Its design was elegantly simple. A sealed cauldron of water was placed over a fire. Rising from this boiler were 2 pipes that fed into a hollow ball, mounted so it could rotate freely. 2 more pipes bent into L shapes protruded from opposite sides of the ball. As the water boiled, steam rushed up through the pipes into the sphere and was forced out through the bent nozzles. The escaping jets of steam pushed back against the ball, causing it to spin rapidly on its axis. It was a pure, working demonstration of reactive force, a principle Isaac Newton would formally define as his third law of motion over 1,600 years later. In essence, Hero had built a steam turbine. For the priests and philosophers who witnessed it, the Aeolipile was a sacred wonder, a symbol of the elemental forces of air and fire made visible. It might have been used in rituals to create awe, or discussed in scholarly circles as a philosophical toy, a curiosity that proved the transformative power of heat. But there it stopped. It spun, it hissed, and it amazed, but it did no work. It turned no millstone, pumped no water, and powered no ship, as engineer John H. Leonhard has observed. The ancient world possessed all the necessary components for a steam revolution: the metalworking, the understanding of pressure, and the mathematical principles. What it lacked was the need, the economic or social impetus to push this temple wonder into the realm of practical application. One significant factor was the widespread availability of slave labor. In an economy where manual work was performed by a vast, unfree population, there was little financial incentive to invest in the complex development of labor-saving machines. The Aeolipile was a solution in search of a problem that Greco-Roman society did not feel urgently enough to solve. The device was forgotten with the decline of Alexandria's great library and workshop traditions, its diagrams preserved only in a few surviving manuscripts. It re-emerged during the Renaissance, a fascinating sketch in recovered texts that inspired thinkers like Leonardo da Vinci. Yet it still took centuries more for that inspiration to bear practical fruit. The contrast is staggering. Hero's spinning sphere of the 1st century and Thomas Newcomen's atmospheric beam engine of the early 18th century operate on fundamentally different principles, one reactive, one using piston pressure. But the Aeolipile represents the seed of the idea, the recognition that steam could create motion. The millennia-long gap between that seed and the harvest of the Industrial Revolution forces a profound reflection. What truly determines whether an invention changes the world or fades into obscurity? It is not merely the spark of genius, for that was clearly present. It is the fertile ground of necessity, of economic structures, and of a culture that sees a tool not as a wonder but as a means to an end. The Aeolipile's story is the ultimate cautionary tale of our entire journey. It asks us to consider a pivotal what if. What if the ancient Mediterranean world had faced a labor shortage or had possessed a driving cultural belief in mechanical progress? Could the whir of steam engines have echoed through Roman factories centuries before the coal smoke of Manchester? The path not taken by the Aeolipile illuminates the delicate, often invisible web of conditions that allows human ingenuity to truly take root and grow. The threads connecting these 15 stories weave a single, haunting tapestry of disappearance. Political collapse, like the fragmentation of the Roman Empire, severed the supply chains and centralized workshops that produced self-healing concrete. Guarded secrecy, the defining strategy behind Greek fire, ensured that when the last artisan died, the formula died with him. Societal needs shifted, rendering the magnificent south-pointing chariot obsolete when a simple magnetic compass offered a more portable solution. These are not isolated accidents of history. They are patterns of loss that repeat across millennia. Historian James Burke has illustrated how technological regression is a real phenomenon, where advanced concepts can vanish from a culture's toolkit, only to be painstakingly reinvented centuries or even millennia later, as if discovered for the very first time. This creates what we might call dark ages in specific fields, periods where progress not only halts but actively reverses. The intricate gearwork of the Antikythera Mechanism represents a peak that European mechanics would not reach again for over 1,000 years. The knowledge of how to build it didn't evolve into something greater, it simply evaporated. Much of what we do know about these lost marvels comes from the patient work of archaeology, piecing together fragmented evidence from shipwrecks, buried hoards, and cryptic texts. Yet archaeology can only recover the physical object, not the living tradition that created it. This highlights a crucial divide, the gap between theoretical knowledge and practical, hands-on application. A manuscript might describe a steam engine, but without the master craftsman who knows the feel of the metal, the sound of the right pressure, that description remains a ghost. Cultural attitudes play a decisive role. In societies where innovation was seen as philosophical play or sacred wonder, as with Hero's organ or Archytas's pigeon, inventions remained dazzling curiosities rather than seeds for widespread practical use. Their survival depended on the continued patronage of a curious elite, a fragile foundation in a turbulent world. Today, we are in a race to rediscover these technologies using cutting-edge science. We peer with electron microscopes at Roman concrete to find its self-healing nanoparticles and use X-ray tomography to map the gears of the Antikythera device. But this modern quest holds up a mirror to our own time. Consider the parallel between the lost formula for Roman concrete and our current reliance on digital data. We have built a civilization on information stored in formats that may become unreadable as software evolves and hardware becomes obsolete. Could future historians stare at a silicon chip as we stare at the Phaistos disk, seeing a container of knowledge with no key to unlock it? This reflection leads to a final, pressing question. What masterpieces of our own age might one day puzzle the future? Perhaps it is not a physical object at all, but a fragile digital ecosystem, a social structure, or an environmental balance we currently take for granted. The greatest lesson from these 15 lost inventions is not about the past's failures, but about our present responsibility. It asks us to consider what we truly value, what we choose to teach, and how we might build a legacy of knowledge that is not just brilliant, but resilient. Human creativity is both a brilliant flame and a fragile ember. Our journey through 15 vanished marvels has revealed not a simple story of primitive ancestors, but a complex landscape where sophisticated understanding in astronomy, medicine, engineering, and material science flickered into existence, only to be swallowed by the long shadows of time. These were not failures of ingenuity. The Antikythera Mechanism proves ancient Greece possessed computational genius. The self-healing concrete of Rome demonstrates a mastery of chemistry we are still striving to replicate. The loss of these technologies was rarely about a lack of intelligence, but about the collapse of the delicate ecosystems that sustained them, the fall of empires, the guarding of deadly secrets, or simply a shift in what a society needed and valued. This collection of stories dismantles the comforting myth of linear progress. History, it turns out, is not a steady climb upward. It is a series of peaks and valleys, of brilliant summits reached and then forgotten, forcing later generations to rediscover the path all over again. Yet within that pattern lies a profound source of hope. Rediscovering these lost chapters does more than correct the historical record. It actively sparks modern innovation. Scientists studying the nanoparticles in the Lycurgus cup are pioneering new medical sensors. Engineers analyzing Roman marine concrete are designing sustainable infrastructure for our coastlines. The principle behind Zhang Heng's Seismoscope inspires designs for simple, resilient earthquake detectors in remote communities. The past, when we listen closely, offers blueprints for the future. This brings us to a powerful insight from the writer Isaac Asimov. He noted that the most exciting phrase in science, the one that heralds new discoveries, is not eureka, but that is funny. It is that moment of curiosity in the face of an anomaly, the puzzled glance at an artifact that should not exist, the question asked about a recipe that makes no sense by modern standards. That is the spirit that recovered these inventions from oblivion, and it is the spirit they invite us to cultivate. How does this change our view of ancient civilizations? It asks us to replace condescension with humility, to look at the ruins of a temple or the fragments of a tool not as relics of a simpler time, but as pieces of a sophisticated puzzle we have only begun to assemble. It invites us to wonder what other masterpieces of thought and craft still lie buried, waiting for a curious mind to say, "That is funny." What forgotten technology from our own age might one day prompt the same question? As we close this voyage through forgotten genius, we leave you with an invitation to keep looking. If these stories captivated you, subscribe to continue exploring the mysteries history has left behind. Let us know in the comments which lost invention reshaped your thinking the most. Was it the ancient battery or the surgical tools of Sushruta? And seek out these marvels for yourself in museums and in the pages of books where the silent legacy of our ancestors continues to whisper its secrets. The journey through time is never truly over, for every artifact is a question, and every question is a beginning.